is Benasrie-Arjoon, formerly known as Miss Benasrie. I'll be teaching you C-Sec chemistry. I hope you're excited to learn. Let's begin. Today's chemistry lesson is called Oxidation-Reduction reactions, also known as redox reactions. We're going to learn oxidation-reduction reactions in everyday life. What is oxidation and reduction, oxidation numbers, and oxidizing and reducing agents. Let's look at some oxidation-reduction reactions in everyday life. And that's not even half of it. Redox reactions are so common they're a part of life. Let's take a look at what the experts say about oxidation and reduction. What is oxidation and reduction? Meet oxygen and hydrogen. They are the star atoms of redox. There are three ways we can define oxidation and reduction. One is in terms of atoms, the other in terms of electrons, and lastly in terms of oxidation numbers. Let's see what our star atoms have to do with oxidation and reduction. Oxidation can be defined as the gain of oxygen. As you can see in this example, the aluminium atom gained oxygen atoms, combining to form the compound aluminium oxide. Hence, the aluminium was oxidized. Reduction, however, is the loss of oxygen. In our second example, copper oxide has lost oxygen and was therefore reduced to copper metal. Reduction can also be defined as the gain of hydrogen. Here we see that chlorine has gained hydrogen to become hydrogen chloride. We can therefore say that chlorine was reduced. Oxidation, however, is the loss of hydrogen. Using the same chemical equation, notice that hydrogen sulfide has lost hydrogen, producing sulfur. Hydrogen sulfide was therefore oxidized. Oxidation and reduction are clearly opposite processes, which you would observe more as we go along. Let's define oxidation and reduction in terms of electrons. Oxidation is the loss of electrons, but reduction is the gain of electrons. Using our previous example, we see that the aluminium has lost 3 electrons as it is oxidized to the aluminium ion in the compound. In the reduction example, 2 electrons were gained by the copper-2 ions as it is reduced to its metal atom, copper. Oxidation and reduction half equations are used to represent these redox processes alone. Hence, it is called a half equation. It shows where electrons have been lost or gained. Here's a common acronym used to remember redox in terms of electrons. Oil rig. This translates to oxidation is loss of electrons, whereas reduction is gain of electrons. The last definition of oxidation and reduction involves oxidation numbers. Oxidation numbers represent the oxidation state of an atom or ion which is affected by electron loss or gain. Oxidation is the increase in oxidation number, whereas reduction is the decrease in oxidation number. Looking at our examples once more, aluminium's oxidation number increased from 0 to +3 in aluminum oxide as it was oxidized. The oxidation number of copper in copper oxide, however, decreased from +2 to 0 as it was reduced to copper. As we've seen, redox half equations represent electrons lost and electrons gained. Notice that electron loss causes an increase in oxidation number, whereas electron gain causes a decrease in oxidation number. Oxidation numbers are what are used to identify redox reactions. Remember that in redox reactions, both oxidation and reduction processes usually occur together. Oxidation-reduction half equations are commonly used in electrolysis. Have you ever heard about electrolysis? In this process, there is no chemical reaction occurring. It is solely a redox process. What happens is that charged ions are attracted to respective positive and negative electrodes that are charged through an electric flow. The ions then lose or gain electrons, changing into their oxidized or reduced forms. Notice that the cations, which are the positive ions, gain electrons, whereas the anions, which are the negative ions, lose electrons. Redox half equations are used to show this change in oxidation state. It's trivia time. Which of the following definitions refer to oxidation and reduction? Use the hint shown, oil rig. Give yourselves 2 minutes to answer this question. You can pause the video now. Go! Time's up. Check your answers. Get it? We just saw that oxidation number represents the oxidation state of an atom or ion. They are used to identify redox reactions. As we've seen, the oxidation number is affected by electron loss or electron gain. Remember that when both processes occur, the reaction is called a redox reaction. This is usually the case for most reactions. As Thanos would say, perfectly balanced, as all things should be. Let's learn how to determine oxidation numbers. Hold up. First, we need to learn some rules. There are several rules for assigning oxidation numbers. Let's look at rule number 1. All elements in their free uncombined state have an oxidation number of 0. For example, oxygen in its free state is a gas molecule. This means that each oxygen atom has an oxidation number of 0. Magnesium in its free state is its metal atom. Here, magnesium will also have an oxidation number of 0. Rule number 2. All monatomic ions have an oxidation number equal to their ionic charge. For example, in the magnesium ion, the ionic charge is 2+, but its oxidation number is +2. Notice where the sign is. For the ionic charge, the sign is always written after the number, whereas with oxidation numbers, the sign is always written before the number. Rule number 3. All hydrogen ions have an oxidation number of +1 except in metal hydrides where it is -1. In this example, we see the oxidation number of hydrogen in hydrogen chloride is +1. But in magnesium hydride, notice it is -1. Rule number 4. All oxygen ions have an oxidation number of -2, except in peroxides where it is -1. Here we see the oxidation number of oxygen in calcium oxide is -2, but in hydrogen peroxide, notice that it is -1. Rule number 5. All polyatomic ions, which are charged groups of atoms, have an overall oxidation number that is equal to its charge. That is, the sum of the oxidation numbers of their individual composite ions will be equal to the overall oxidation number. Here we see the polyatomic ion sulfate with an oxidation number of -2 since its ionic charge is 2-. Rule number 6. All compounds have an overall oxidation number of 0 since they are neutral substances. That is, they have no charge. The sum of the oxidation numbers of the individual composite ions will therefore be equal to 0. In this example, we're using magnesium chloride. Notice there are 2 chloride ions with an oxidation number of -1 and 1 magnesium ion with an oxidation number of +2. To calculate the overall charge of magnesium chloride, we add the oxidation numbers of the individual composite ions, which is 2 plus 2 times -1 since there are 2 chloride ions, and that equals to 0. Rule number 7. Use known oxidation numbers to calculate unknown oxidation numbers. We know the oxidation number of oxygen in sulfate is -2. The overall oxidation number of sulfate is also -2. So what is the oxidation number of sulfur in the polyatomic ion? We let a number be x. We can therefore say that x plus 4 times -2, since there are 4 oxygen atoms in the ion, will be equal to -2, which is the overall oxidation number of sulfate. Hence, the oxidation number of sulfur in sulfate is equal to +6. Rule number 8. With the exception of hydrogen and oxygen, atoms in covalent compounds and polyatomic ions have varying oxidation numbers. Here we can see the oxidation number of nitrogen in ammonia is -3, but in nitrogen dioxide it is +4. Notice also the oxidation number of sulfur in sulfate is +6, but in sulfite it is +4. Rule number 9. Transition metal ions have varying oxidation states in different compounds. Their oxidation state is included in the compound's name. For example, copper-1 oxide means that the oxidation number of copper is +1, but copper-2 oxide means that the oxidation number of copper is +2. Rule number 10. Psych, you just need to remember all 9 rules. It's trivia time. Calculate the oxidation number of chromium in the chromate ion shown. Here's a hint. Let the oxidation number of chromium be X. Once again, you have 2 minutes to answer this question. You can pause the video now. Go! Time's up! If you calculated the oxidation number of chromium in the chromate ion to be +6, then you're correct. Oxidizing and reducing agents. What is an oxidizing agent? The substance causing oxidation, of course. An oxidizing agent accepts electrons that are lost from another atom or ion, causing oxidation while becoming reduced in the process. A good oxidizing agent must be good at accepting electrons, such as nonmetals. What is a reducing agent? Of course, it must be the substance causing reduction. A reducing agent loses electrons for another atom or ion to gain, causing reduction while becoming oxidized in the process. A good reducing agent must be good at losing electrons, such as metals. Welcome to the virtual lab. Let's explore some redox reactions. First, we'll be investigating some common oxidizing agents. Potassium permanganate, which is KMNO4, and potassium dichromate, which is K2Cr2O7, are both very strong oxidizing agents. They are commonly known as potassium manganate 7 and potassium chromate 6. We'll also be investigating aqueous iron tree salts, which also act as an oxidizing agent. Other examples include oxygen, chlorine, hydrogen peroxide, and sodium chlorate, which is a key ingredient in bleach. Redox reactions usually show visible changes such as color change, effervescence, which is the evolution of gas, or precipitates. When potassium manganate 7 oxidizes a substance, it changes from its purple 7+ ions to its colorless 2+ ions. Remember that an oxidizing agent also becomes reduced when it oxidizes a substance. Similarly, potassium chromate 6 changes from its orange 6+ ions to its green 3+ ions upon oxidizing a substance. This is the reaction used in the breathalyzer test. Breathalyzer tests are used to detect the presence of alcohol in a person's breath. Potassium dichromate crystals contained inside the equipment changes from orange to green once alcohol is blown through. That is, it oxidizes the alcohol and is in turn reduced from its orange 6+ ions to its green 3+ ions. When iron 3 ions are used as an oxidizing agent, the color change observed is from brown to pale green. This is the color of its iron 2 ions. You would also notice that most of these oxidizing agents consist of oxygen atoms. Here are some common reducing agents. We'll be investigating the first three, which includes aqueous iron 2 ions, potassium iodide, and hydrogen sulfide. Other examples include hydrogen, sulfur dioxide, and reactive metals. When iron 2 ions reduces a substance, it changes from pale green to its brown 3+ ions. Remember that a reducing agent also becomes oxidized when it reduces a substance. When potassium iodide reduces a substance, it changes from colorless to brown. This is because the iodide ions have in turn been oxidized to iodine in the reduction process. Hydrogen sulfide is a gaseous reducing agent which changes from its colorless gas into a yellow precipitate when it reduces a substance. The precipitate formed is solid sulfur, which is produced as the hydrogen sulfide is oxidized in the reduction process. Let's put your investigative skills to use with this DIY experiment. That's right, you can do it yourself with an adult. But first, let's talk about safety. You must wear personal protective equipment to stay safe when doing any experiment. In this experiment, you'll need to wear a laboratory coat, safety glasses, and a pair of gloves. So be sure to gear up before trying this experiment. Here's what you'll need: red lavender, bleach, a transparent glass containing about 75 ml of water, 2 droppers, and another small glass to pour the bleach into. We're going to add a few milliliters of red lavender into the water until it forms a uniform red color. You can stir to achieve this faster. Next, we're going to add some household bleach dropwise until we observe a color change. Red lavender is an essential oil with a distinctive red color. This, like many other colored essential oils, turns brown when oxidized. The resulting brown products formed are not safe to use and must be discarded. Oxidation of essential oils happens after long periods of exposure time to oxygen in the air. This is when the product expires. Here we sped up the oxidation process using an oxidizing agent called sodium chlorate. This is the active ingredient in bleach. It's that strong. Ever wondered why you're instructed not to mix bleach with any other cleaning agents? This is because the bleach can oxidize the substance, which can potentially form hazardous gases and can therefore cause us harm. So don't mix your cleaning agents with bleach. Hydrogen sulfide and sulfur dioxide are both gases found in high concentrations nearby volcanoes. Notice that both of these are reducing agents. Some reducing agents act as oxidizing agents in the presence of stronger reducing agents. This is what is happening in this reaction. The sulfur dioxide in this case is acting as an oxidizing agent since the hydrogen sulfide is the stronger reducing agent. Looking at their oxidation numbers, notice that sulfur in hydrogen sulfide has been oxidized from -2 to 0 as sulfur is produced. This confirms that the hydrogen sulfide is the reducing agent. In sulfur dioxide, however, the oxidation number of sulfur has been reduced from +4 to 0, confirming that sulfur dioxide is the oxidizing agent in this reaction. Remember that when hydrogen sulfide acts as a reducing agent, it becomes oxidized to sulfur, which is a yellow precipitate. This is why yellow sulfur deposits are seen surrounding active volcanoes. Similarly, some oxidizing agents can also act as reducing agents in the presence of stronger oxidizing agents. Here we have hydrogen peroxide and potassium manganate 7, 2 oxidizing agents. When one is added to the other, the potassium manganate 7 changes from purple to colorless. This indicates that the potassium manganate 7 oxidized the hydrogen peroxide, which acted as the reducing agent in this case since it was the weaker oxidizing agent. Tests for oxidizing and reducing agents. Simply add a known oxidizing or reducing agent and observe what happens. The color change or precipitate formed will tell you. It's trivia time. What are the oxidizing and reducing agents in the reaction below? Here's a hint. Determine what was oxidized and what was reduced. Give yourselves 2 minutes to answer this question. You can pause the video now. Go! Time's up! If you had copper sulfate as the oxidizing agent and zinc as the reducing agent, then you're correct. Wasn't that interesting? The next time you see a rusty old car, or you're walking past a building covered in rust, even when you're doing the laundry, or biting into your fruit as it turns brown, you'll know that these are everyday examples of oxidation-reduction reactions. You should now be able to teach your friends and family what is oxidation and reduction, recall all about oxidation numbers, and discuss oxidizing and reducing agents. That'll be all for today's lesson. I hope you feel inspired to go observe some examples of oxidation-reduction reactions wherever you are. You'd be surprised. Until next time, bye!